in fact, part of what I'll be discussing today is, I think, the first official collaboration between, INSI London and INSI Boston with Salvo. I think, can I check if everyone in the room is from INSI, or are there outside attendees? Let's say, no, everybody is okay. So I don't have to explain what INSI is. So what I'll be discussing today is, so I'm there in London, just maybe, I don't know if all of you know, we have a group of about 30 researchers at the moment. It's me and Vipin Rajendran co-directing the center. And we are focusing on aspects related to AI and reliability and computing and efficiency. Things like neuromorphic computing, quantum computing. We are in the east side of the city. If you'd like to visit us, it's a nice place. And we always welcome visitors from Boston. And so what I'd like to talk about today is the problems that go along the following line. So you decided to use AI for your telecom network, and I think a lot of people here at INSI do that. And so you run your network, you get some performance measures, KPIs, key performance indicators. And at that point, you'd like to run some diagnostic tests to see how well that AI model and the entire pipeline that led to selecting that model worked. And one way to do that is to try to address a what-if question. The question is, what if I had chosen a different app, maybe a different scheduling app, or if I had configured my system in a different way, or if I had expressed my intent to an agent in a different way. So what we will do here is to try to develop a machinery to address these type of questions. And I am an information theorist, I work also in statistics, and we will see that in order to answer these type of questions, you cannot use the conventional tools that you are used to probably from machine learning, so prediction tools. Those are not reliable. They don't provide you with any kind of guarantee that they will work well. You have to use more sophisticated and complex techniques which pertain to the field of counterfactual inference. So we will talk about this topic here. And I don't think I need to justify why I care about AI for telecoms, so I'm going to just skip the slides where I motivate why AI is important for telecommunications. I think you know that, right? So you know that NVIDIA invested a significant chunk of money into Nokia because they believe that AI can be important for the RAN, for the radio access network. You also know that we are moving towards this disaggregated deployment of networks where hardware is decoupled from software and software can be running AI applications. That's what motivates this approach. And you also know that the ORAN is standardizing the interfaces that you need for these different software pieces to interact with each other and interoperate. You know this, so I will not explain it in any detail. So I will be focusing on two different types of settings. So the talk is divided into two parts. The first part, I will be looking at what I'll call here a policy-based approach. So the idea here is that you have a policy that the network operator has designed by hand or just trained, and this policy selects the best apps, the best AI applications to run in your network to carry out different functionalities. I don't need to explain what the different functionalities are. The point here is that there is some policy that somebody has designed that looks at the network conditions and chooses the right apps to run. So I call this the policy-based approach for AI for RAN. And so this is the first setting I'll be looking at. The second setting I'll be looking at is an agentic setting. So here, instead of having a pre-trained policy or a pre-designed policy that automatically chooses these apps based on measures from the network, here you have an agent or multiple agents, right, that based on a natural language intent from the operator determine a sequence of executable steps that can be executed by the network. Right? So of course here at INSI there's been quite a lot of work on this topic, and we were inspired in fact by this line of work. So again, the idea is that you have a network operator, expresses some natural language intent, serve these many users, making sure that over this period of time they obtain this level of quality of service. Then you have some agents, one or more, that decompose this intent and decide what to do. Essentially, then in the network these actions are executed, and then some KPIs are measured, and then the agents again look at these KPIs and then provide the operator with a final report, maybe in natural language, saying, things went this way, your intent was implemented, and we got this type of performance. So again, I'll be looking at these two settings, policy-based and agentic. And in both cases, I want to answer a what-if question. So in the case of policy-based system, the question looks like this. Again, you have your policy pre-designed that looks at the set of the apps that you have access to. By apps, I mean pieces of AI, possibly designed software, right? Some code base with a bunch of choices. So your policy looks at the network conditions, looks at the requirements, and chooses a number of apps to run in the network, right? And it collects some KPIs, key performance indicators. The throughput was this much, the delay was this much, and so on. The question is, then the operator looks at these KPIs and says, okay, but what would have happened if I had chosen, under exactly the same conditions, different apps? Right? What would the KPI have looked like? So if I, instead of using the scheduling algorithm, I use the other scheduling algorithm, what would I have gotten then? It's a tricky question to answer as we do so. So this is for the policy-based setting. For the agentic setting, instead, the what-if question is a bit different. So here, again, you have the operator has expressed an intent to the agents. The agents have acted on this intent. And the question is, what if I had expressed a different intent? So for instance, I had phrased it differently. Right? I wanted to say, I wanted to get some results, but I could have phrased the same intent in a different way. Or I could have simply, or I could have expressed an intent that is quantitatively or qualitatively different. Right? For instance, requiring different type of goals or targets for the system. So the question here is, what if I had expressed a different intent? What type of report would I have gotten back from the network? Right? I know what I got factually for the intent that I've chosen. What would I have gotten if I'd chosen a different intent? So the two questions are, of course, the same question. It's what if questions in both cases, but the settings are different. And we will see we'll need different tools to deal with these two questions. By the way, at any point, if you want to ask questions, feel free. Okay. And so one of the main messages of this talk is that you cannot just use conventional predictive machine learning to address this type of what-if questions. In fact, the tools that we need sit on top of what Joshua Pearl called the inference ladder. So at the bottom of this ladder, you have conventional prediction. So there you look at the data, you have input, I call the input A for action, for app, action, and the output Y. So you look at your data and you find which Y's are more correlated, which values of Y are more correlated with A. So this is purely associative thinking, right? So there is no causality involved, it's purely correlation-based reasoning, right? So that's the conventional, when you train a predictor, that's what you're doing, right? You're looking at associations in your data. So Pearl calls this C, because you're looking at the data. On top of that, there is intervention. So here, you're not just looking at the data and see what type of correlations are present in the data, but you're talking about causality. So you're asking, what if it's not what if. You want to understand the type of Y's that you get if you act in a certain way. Right? This is very different from just looking at the data and see what happened when A happened. You want to know what type of Y's you get if you set A in a certain way. So that's intervention, which sits on top of that. And on top of that even, we have counterfactual, which is what we care about. So here, you chose A, and you observed Y. And then you ask, what would Y have been if I had chosen A prime? And it's even more complicated than intervention. And the point of this ladder is that if I want to solve this one, I need to be able to solve the bottom ones. So each one subsumes the previous two. And so we are sitting on top. And again, the question is, can we answer this type of counterfactual or what-if questions? And the key challenge here, of course, is that you cannot go back in time. Right? So if I wanted to know what if, and if I had a time machine, I could back in time, do those actions, and see what I would have gotten. Right? The problem is that I cannot do that, and so I need to be able to answer these questions without rerunning the system, right? Without being able to recreate the same conditions that were there when I factually made certain choices. Does it make sense? Yes.
Just your underlying assumption here is that you have a physical system where you cannot go back in time, because if you have a simulator, a digital twin, you can do whatever you want because you can rerun experiments in a controlled way.
Yes. So in fact,
so you're assuming the first, a physical system.
Yeah. So exactly. So we'll discuss that later. In fact, if you have a simulator, for instance, what you can do is that you run it, you record the random seed, for instance, that you use to run the system, and then you run it under exactly the same conditions. Absolutely, you can do that. In that case, the problem will be solved, essentially. The issue, of course, is when you have a system that you cannot, for which that does not apply, right? For which you cannot just, I'm running my network right now, certain conditions underlie the current deployment. I cannot somehow record perfectly all these conditions and rerun the system again. Okay, any other questions? Okay, so let's look at these two settings. One is policy-based, the other one is agentic. And in the first case, the question is, what if I had used a different app? Right? So what if I had chosen a different app? What if my policy had chosen a different app? So to fix the ideas, I'll look at this example because it is a very common one. So here the problem is scheduling. Okay, I don't need to explain to you what scheduling is. Scheduling means that for instance, for the uplink, you want an app that looks at the current state of the queues of the users, looks at the current channel conditions, and determines which UEs, which user equipments, get to transmit when, right? Which type of resource blocks are located to which users, etc. So this is a classical problem, of course, at level 2, right, of network. So in a policy-based system, you will have a policy that looks at the current conditions, looks at how many packets there are, what these users require, what type of services they're running, looks at the current channel conditions. I call that the context, X, and based on that chooses an app, an application, A scheduling algorithm. Okay. And just to fix the ideas, maybe your policy could work like this. If I'm not sure this is a particularly good idea, but it's a potential policy could work like this. It could look at the channel conditions and the queue conditions, and if the conditions are homogeneous, all users more likely to do the same, then maybe you can use round robin. So that means you give the same access to every user in a round robin way. Whereas if conditions are heterogeneous, different users have different channel conditions, and they have different requirements and so on, maybe you want to use something more sophisticated, like proportional fairness, which instead tries to boost the throughput while maintaining some fairness. Okay. It's just a potential policy, could work like this. What I'm discussing is completely general, of course, but just to give you a sense of what a policy may look like. And so let's say, given conditions X, a certain app is chosen. Maybe we choose proportional fairness and PF. You don't need to know what proportional fairness is. So we choose PF, and then we measure the KPIs. Maybe we measure the how many packets are left at the end of some period of time. If when I choose PF, proportional fairness, and then I ask, okay, well, what if instead, under exactly the same conditions, I had chosen round robin, right? What would the backlogs be if what you care about are the backlogs at the end? So the number of packets at the end of a certain period of time. In general, you not only want to have a point estimate, so you want to say, you have this many packets at each device, or again, you can care also about other KPIs if you like, but you also want to provide a measure of uncertainty, because the estimate is not going to be perfect, so you also want to be able to say, how accurate that estimate is. So this is the general problem. And just to generalize it, to frame it in the most general form so that it can be applied also beyond this setting. So as I said, you have a context vector, which has some distribution. For instance, for scheduling, this could be the current channel quality indicators, backlogs for all the users. So this is what the policy knows to make an informed choice about the app. Then the policy chooses an app, right? So you have a policy, I call it P of A given X. So it's a conditional distribution. The given X chooses A. We need to model it as a distribution for generality. For instance, this could be, for those of you who know, could be maybe a softmax output for a training policy. It gives you some probability of choosing every app. For example, it may look something like this. If X is a homogeneous context in the scheduling case, then the policy may do something like this. With higher probability, it chooses round robin, and with some probability, it also chooses proportional fairness. Just an example. Okay. So the variables here are X, it's the context, A is the app. Then there is the KPI, or the KPIs. So the KPI depends on the app that you've chosen, right? So I write that, this is very common in this literature, you write that as YA. So that means the KPI that you get if you choose action A, if you choose A, app A. And this will have some distribution. I drew here some whatever distribution. That depends on the context in general, right? So this could be the backlog, the final backlog of the users, and the maximum backlog. And it will have some distribution that depends on the context and on the action that you're doing. And so the variables that we have are these three: X, A, and Y. Right? Y is the KPI, A is the action, and X is the context. And the question we're trying to solve is this. Now, under context X, the policy chose a certain app, chose, for instance, proportional fairness, and we observed a certain KPI. And the question is, what if we had chosen a different app, round robin, right? What would the KPI have been then? The fundamental problem here is that this is the factual branch. So this is what happened in real life, right? What we want to know is something about this counterfactual branch. So this is what did not happen. And as we were discussing before, I cannot just go back in time and make it happen. So that's and the fundamental problem here is that if you look at your data, you never observe this counterfactual branch. This is what is called the fundamental problem of counterfactual inference. So if you look at your data, you only observe what actually happened. Right? So you only observe this branch, right? What actually occurred. You never get to observe what could have happened. Right? And that's the key problem. That you only observe terminologies, you only observe one of the possible potential outcomes. So that's the problem that people have to worry about in this field of counterfactual inference. So there are different frameworks that we can apply, and for this setting, the most basic framework is the so-called potential outcomes framework, which is a standard concept in statistics. You can read about it in standard textbooks if you like. And the idea is very simple. The idea is I'm just going to treat the outcome, Y, for each action or app A, as a separate random variable. I'm just saying, okay, for every app, there will be some KPI, and I'm just going to treat these KPIs as separate random variables. And I'm not going to even try to figure out what the correlation between these variables is. I'm just going to say there are different variables, each one has its own distribution, and that's all that I'm going to do. No, I'm not going to make any kind of fancy model. I'm just going to treat them as separate. So this is the potential outcome. It's called potential outcomes framework because each one of these YA is a potential outcome, right? That you get if you chose a particular action. So under this model, what is typically done is this: you offline, you collect data, and you train a predictor for every potential outcome. For every app A, you train a predictor. As you will see, this is not that simple. You cannot just do the usual thing to do training. And then as a second step, what you want to do is you want to calibrate this predictor to be able to provide some confidence intervals on the KPI. So let's see how this is done. So remember that the data that we have access to is of this form. You have the context, X, the app that you chose, and the KPI that you got. And you know the distribution of the app given the context. You know it because it's your policy. Everything else you don't know. But this one you know. This one in red, you know it because it's the policy that you're running. So that you can use as a fact that you know. So just to give you an example, the data that you can collect is of, looks something like this. This is a small data set that I just randomly generated. So in this data set, what you have is the context, and in this case, I consider the scheduling setting with two apps for two UEs, two users. So maybe this the first two numbers represent the channel conditions in some scale, CQIs, and this one represents the number of packets that these users have in their queues at the beginning of time. Just an example. Okay, so you will have a context vector for every data point. So that's what the policy saw when it decided which type of scheduling algorithm to use. So you've got that one in your data set, X. You get the app that was actually selected. It could be, in this example, just round robin or proportional fairness. Instead of simple K. And then you record the KPI, which in this case is, I am thinking of it as the backlog at the end of some period of time for the users, maybe the maximum backlog. Okay, so we've got X, A, and Y in the data set. In here, I also classified, so that we can think about the problem, these different contexts as being either homogeneous or heterogeneous. So homogeneous means, the two users more or less have the same conditions, and heterogeneous means they have different conditions. I'm doing this just because, if you remember, I'm thinking of a policy that if the context is homogeneous, tends to select round robin, and if the context is heterogeneous, tends to select proportional fairness. So you see here, for instance, this context is homogeneous. Whenever the context is homogeneous, most of the times we choose round robin, sometimes we choose PF. And if the context is heterogeneous, most of the time we choose PF, but sometimes we choose round robin. That's just how the policy works, right? That's how I designed the policy for the example. Yeah?
Is the type of context only important in this specific example or in general?
So in general, you have some context, right? And in general, the choice of the app or the action, or general event, will depend on the context. So I added this column just to remind ourselves that whatever is in this column depends on this column. Because depending on the context, we choose the app. So is it clear? Okay, so this is what creates the whole problem, right? This dependence between X and A is the whole problem of counterfactual inference. Let's see why. As I said, under the potential outcomes framework, we want to train a predictor that given X, so given the context, predicts the backlog, right? And I want this predictor to work in general, right, for any context. Now let's see if we can spot what the issue here is, right? So how can we train a predictor that given X predicts Y, and I want to do that for every app, for every action A, I want a different predictor. So for instance, let's say I want to train a predictor for round robin. So I want to have a predictor that given context X tells me the backlog that I get if I use round robin. Okay, so I go to my data set and I select only the data points in which round robin is used. I have to do that, right, because those are the only cases in which I observe the backlog for round robin. Right, so I have to go into my data set and do a selection where I only select the rows corresponding to the case where I actually run the app whose KPI I'm trying to predict. Now, let's see if you can spot a problem here. So I want my predictor to work for any context, right? Under any general context, X, right? Because given X, I want to predict Y. But if you look at the data set that I have access to, what's happening is that the contexts that are represented in my data set are skewed, right? Most of these contexts are homogeneous because those are the conditions under which round robin was selected. That means that other types of contexts, let's say heterogeneous ones, are underrepresented. So the predictor that I get, if I train on this data, would maybe work very well for homogeneous contexts and work very poorly on heterogeneous ones. Because simply these type of contexts are underrepresented in this data set. Okay. So that's the fundamental problem that we have, and this is called selection bias. So the problem is that the data that I have access to train has some distribution, which is really the distribution of the context given the app, right? But I want my predictor to work for any context that have any distribution, let's say the marginal distribution, not the conditional distribution. So this is a covariance shift problem, right? You want your data to have some distribution, but unfortunately it has a different distribution. And how do we solve this problem? And that's basically the end of the story here. You can use something, and this is the picture, right? So I'm training a model, and I have data that has this type of distribution, because, for instance, if I choose round robin, most contexts are homogeneous. But in fact, I would like data that covers the entire spectrum of contexts, because I want a predictor that works irrespective of the context. So how do I solve this problem? You may know there is a method, standard method called importance sampling. The idea is that, okay, I would like my data to have this distribution, which is, let's say, the unconditional distribution of the context, right? Not conditional in any app. But I only have it for this distribution, which is conditional on the app. If I somehow can figure out this ratio, then I can also figure out which contexts are overrepresented or underrepresented in my data set, right? So, for instance, if this weight is high, what does it mean? It means that this distribution, which is what underlies the data I actually have, is smaller than this. And so that means these data points are underrepresented in my data set. Whereas if the weight is low, that means the data points are overrepresented. And so then, if I am able to calculate this weight, what I can do, when I build my training loss, right, instead of just treating all data points the same, right, instead of looking at my data here and treating all these guys the same way and do a conventional average when you calculate the training loss, what I'm going to do is I'm going to downweigh this homogeneous context because they're overrepresented. So I'm going to multiply them by a small number, so they weigh less in the training loss. And I'm going to upweight this heterogeneous data point because it's underrepresented. Okay. That's the idea. So the idea is that for every data point that has context X, I take the loss and I multiply by this weight. So this compensates for the covariance shift. And in fact, you can prove, it's very easy to check, that this becomes an unbiased estimate of your loss. So by upweighting and downweighting, you make sure that even though you have this selection bias and this covariance shift, your training loss is unbiased. And so therefore the predictor that you get now follows the standard, let's say, approach on machine learning to minimize an unbiased objective. There is a problem though, and the problem is that, as you can see here, in order to calculate the weight, I need to know the ratio between the true distribution of the context and the distribution of the context conditional on the action, which of course I don't know. No way I can know this. But if you use Bayes' rule, it's a simple exercise, you can check that you can write it like that. And now, this is very nice because the denominator, we know it, it's your policy. The numerator, we don't know it, but it doesn't depend on X. So it doesn't matter because at the end we are minimizing this, we are minimizing the sum of terms like that. So if there is a constant, that constant doesn't matter at all in the training loss. So the point is that what you can do simply is that you take any training point and you divide it now by the probability of selecting the app that you care about under that context. And this is called inverse probability weighting. So it's very simple. Maybe the story is a bit complicated now, but very simple. You take every data point here in your data set, and you look at the probability of selecting this app under this context, and you divide that data point by that loss by that probability. That's it. And this you can do very easily, and you can also show that this is also unbiased, and so that's basically the end of the story. So to solve the problem of counterfactual training, let's say, you have to use inverse probability weighting. Okay, then there is another problem. The problem is that now you get your predictor. Let's say you have selected a certain app. Now you want to know what would have happened if I chosen a different app. Okay, now you have a predictor for that. Right? So for instance, I want to know what the KPI would have been if I had chosen round robin, for instance, okay, the A prime is round robin. Now I have a predictor for that. So the predictor will tell me that under the current context, maybe this is the distribution of the KPI. That's whatever the predictor that I trained, maybe something like this, right? Now, once I have a predictor like that, you can say, for instance, I can use this one as a point estimate. So I can say, okay, I think the KPI will be this one, the mean. But of course, that doesn't tell me anything about the accuracy of this predictor. It could be bad, it could be very accurate, not very accurate. What you also want to do is to give a confidence interval. Right? You want to be able to say that, okay, your KPI, so the backlog you would get, for instance, if you had run round robin, will be in this interval with 90% probability. So you want to be able to provide a confidence interval. So often we use machine learning without worrying about confidence intervals, but that's very misleading, because in that case you have no idea what the accuracy of that prediction is, right? So ideally you want to be able to say, okay, your output is here, and I can tell you it's there with 90% chance, about 1 minus alpha. And so it looks like this is quite easy. So it looks like, okay, since I have this predictor, I can just find an interval such that this area is 0.9, and I am done. Right? Unfortunately, that doesn't work at all. And the reason is that this is just a predictor. It's not the true distribution. Right? So you cannot trust that predictor to represent the true distribution of your KPI. And this is the famous problem of miscalibration. So what this entails is that if I just trust the model, then my actual output could easily be outside this interval with any probability, definitely more than 10% that maybe I'm targeting. And you may know this problem of miscalibration is very important also beyond simple predictor models like this. For instance, this is maybe you've seen this is a chart from OpenAI, which shows the gap between the probabilities that this was for GPT-4. So this is the probability produced by GPT-4, and this is the true probability of a certain outcome. And as you can see, there is a huge gap. So maybe GPT is quite accurate in terms of point estimates. Maybe it gives you a correct answer 80% of the time. But if you ask it to quantify its uncertainty, there is a huge gap, and that's a big problem. And the bottom line is you cannot trust the probabilities that the model gives you. So you cannot build confidence intervals just by looking at the probability of the model. Yes?
So is this uncertainty tied to, so we have seen that you have like the table with the context, and then you train that you can like do the estimates based on the context and the results of like what was the outcome. What happens when there is context that is missing? Is the model able to fit or do some sort of interpolation to estimate that, or is missing data that cannot be recovered?
So yeah, so when you use inverse probability weighting, a key assumption you're making is that that policy cannot be equal to 0, because otherwise you have to wait for an infinite amount. So this means that your policy has even a small probability of selecting any app under any context. Of course, if that probability is very, very small, that means in order to get a good estimate, you'll need more data, because you need to be able to see that context represented. So yeah, so your point is well taken. When you apply this method, first of all, you need to assume that the policy, it's called a positivity assumption, that it can select any app, even with small probability. And the smaller that probability is, the more data you will actually need to be able to see that context. It's one of the key problems.
So basically you have two data sets, and you train one data set, and you readjust the predictor with the other data set.
So I have not discussed the adjustment yet. So for now, we just have one data set. We use that data set to train one predictor for every app. That's it. We will see now that we need another data set. But for now, we just need one data set. It's just that when I use that data set, instead of just using these data points as they are and giving the same weight to each one of these, I'm going to assign a different weight to each one of these data points. And that weight tells me how likely it is for this app to have been selected under that context. But it's one data set only.
just understand the problem of miscalibration. So if you were to have an infinite number of samples, like with each like condition covered very well, would we still have the problem of miscalibration?
Yeah, okay, so let's say if your model is very flexible, let's say for instance you use a histogram with many, many beats, right? And if you have a lot of data, eventually miscalibration disappears, right? Because the model becomes consistent. But in practice, you have to use a parametric model, and you have limited data. So this problem of miscalibration has been reported for even the most advanced LLMs. So it's very difficult to get rid of. Any other questions? Okay, good. So how do we solve the miscalibration problem? I will not really spend too much time on this because I could do a long lecture just on this. But the idea is we can use something called conformal prediction. So the idea of conformal prediction is not that difficult to understand. So remember, you have your predictor, but we don't trust it. We don't trust the probabilities. So instead of just, again, defining this interval, this confidence interval, looking just at the predictor, what we're going to do is we're going to set a threshold here and determine the interval, the confidence interval, as all the values of the KPI whose density under the model is above some threshold. The whole problem is how to select the threshold, right? And to select the threshold, what we do in conformal prediction, we keep aside some data. So we have our data that we use for training, fine. Now we need another data set that we use just for calibration that was never used for training. And this data set is used just to select this threshold. And the key idea is that basically you want to find this threshold in such a way that when you look at the empirical coverage, so you look at what is the fraction of examples in which the true counterfactual, the true KPI was in the interval, you want this fraction to be 1 minus alpha, which is your target, for instance 90%. In order for this to work, there is a small correction that you need to apply, but essentially it is looking at this calibration data set and making sure that empirically the coverage, so the 90% target, is satisfied on that data set. And interestingly, this is enough. So if you do that, you can guarantee that indeed that interval gives you the 90% requirement or the 1 minus alpha requirement that you want. However, in counterfactual inference, as usual, things are not that simple. So this is conformal prediction, or conventional prediction. In the case of counterfactual, unfortunately, you have this covariance shift, right? Because you are looking at data, again, that is only being collected on some types of context. And so, again, you need to compensate for that. And you can use importance sampling. I will not get into many details here. It's the same thing we discussed before. Basically, we need to compensate for the fact that our data follows some app, but I care about another app, which is what I actually selected in the factual branch. So this is called weighted conformal prediction. It's basically the same problem we saw before. We have the same problem also during calibration, so we need to deal with it in the same way, essentially. Okay, let me show you an example of how this works. So I'm comparing 3 different techniques. The first technique, just trust the predictor. So you train your predictors, one per app, and you just trust it to find the intervals. The second one, you use conformal prediction, but you don't worry about the shift, the covariance shift. So you just use conformal prediction without doing importance sampling. Just trust that conformal prediction will do the right thing. And then the last one is you do everything that I discussed. So you do calibration and you take into account the covariance. And I'm going to study again this scheduling problem, and we used an emulator that Nokia made available online. So that's what we used. I'm sure we could do something more sophisticated. And just to give you a sense of what happens, so here I have a bunch of users. This is the true final backlog, right, for the counterfactual app. So this was a simulated setting, so I can find the true counterfactual, because I can just run the model again, the system again, and see what the true counterfactual was. So the true counterfactual were blue lines, right? And what you see here are the intervals that I get if I use different schemes. So, of course, I would like my intervals to include the two counterfactual backlog, right? What you see here is that this one in this color, whatever they call it is, this is when you just trust the model. You just train the model, trust it. As you can see, these intervals almost never include the true output. So these are poorly calibrated, you cannot use them. If you do calibration, but you forget that there is a shift, a very shift, this is just an example, but you see there are many, across a number of users, these intervals also don't include the true output. For instance, this one. If instead you do the right thing, so you don't trust the model, you calibrate it, and you take into account the covariance shift, then in this example you can cover all of the true backlogs. This is just an example, but of course you can also do some analysis. For instance, here what we did is we look at how many times that those intervals cover the true counterfactual, and these ones in green this is the performance if you just trust the model, and it never reaches your desired coverage, which was 80% here. So basically, trusting the model is a horrible idea. What we changed here is the selectivity in the policy. As we move this way, the policy becomes less and less selective. So it chooses kind of the same apple all the time. And here you see the difference between a scheme that uses takes into account the covariance shift that doesn't. So if you don't, again, you are below your target coverage. So here is 80%, not 90%. You cannot be satisfied. So the bottom line here is that if you do counterfactual analysis, you need to, if you use the potential outcomes framework, you need to make sure to account for the covariance shift both during training and during calibration. Okay. Any questions?
Is there any assumptions on the covariance shift?
So no, there is no assumption. The only thing that we are assuming is that you know the policy. So you know that P of A given X. So you know with what probability every amp is selected under any context. That's the only assumption.
Okay, so these can be completely different, the calibration data set and the training data set that can be.
So yeah, of course the assumption is that both training and calibration data sets, both training and calibration data set follow the same distribution.
But they should have the same context.
The same context distribution P of X. So there is no, so the covariance shift is purely here caused by the policy, not by the environment. So the environment is stationary. The covariance shift is caused by the fact that you are selecting policies differently. Of course, if you add also some covariance shift because of non-stationarity, you should account for that too in your weights.
So I was thinking of a closed loop system, and if that causes change in the output, and this happens over time, so is this one?
So again, if there is a covariance shift due to the environment change, that means that this P of X will change, for instance, in calibration. And so in that case, you have no choice but trying to estimate that covariance shift that happens within the environment. Here, the covariance shift happens because of the policy, so we don't have to estimate it because we know it, because the policy is known. That's the key advantage. But for an environment shift, you have to estimate it. Right? So there are other techniques that we put in place. Any other questions? Okay. So I realize that I'm running out of time. I hope I can take 10 minutes to just run through the Agentic system, which is the work we did with Salvo. So it'd be nice to talk about it for 10 minutes. Okay, so here the setting is what I described. You have your operator expressing an intent, an agent realizing this intent into executable steps, measuring then the KPIs coming from the network, and coming back to the operator with a natural language report. And so the problem we are facing is this one. Okay, we have our A now is the prompt, right? Before it was the action with the app. Now the input is a prompt. An LLM decides on a number of steps, KPIs are measured, and then another LLM comes back with a report. So now the variables of interest here are the prompt and the final report that the agent gets. Yes?
For Why don't you use the KPIs as output?
You can also do that. You can also directly use this KPI as an output. What I want to highlight here is the complications that arise when you have to work with counterfactuals that are in the form of text. Of course, you can also do the same and use the same methodology there. But what we wanted to focus on here is what happens if the input is text and the output is also text. So it's much more complicated. And so the counterfactual problem is this one, right? So you now express a different intent, the system does its thing, and you get a different report from the agents. And you want to figure out, if I express a different intent, what would the report look like? What would the text look like? So this is much related to what we've done in the previous section. So in the previous section, remember, we had an app. Now we have a prompt, but it's still an action that you take. In the policy-based setting, we had a KPI for every act. Here you have a report, some text that the agent gives you back for every prompt. In the case of policy-based, we had a context. Here, for simplicity, we did not have that. So, in other words, the prompt doesn't depend on any kind of external conditions, but that can be also integrated in the framework. We did not do that for simplicity. What we wanted to focus on is this problem that Peter just mentioned, that now the key difference is that before, we had a bunch of apps, a few apps to choose from. Now the input is a prompt, natural language, basically an infinitely dimensional space. The output before was a vector of numbers, KPIs. Now it's text, again, infinite dimensional space. And so the consequence here is that the techniques that we used before cannot possibly apply here. So what we did before, if you remember, is for every possible action A, we designed a different predictor. Right? That's potential outcomes framework. We looked at our data. For every possible action that we take, we train the predictor. Here, this is not possible, right? Because an action is a prompt. So how can you possibly train a different predictor for every prompt? It just doesn't make sense. So that means we need to do something more. We need to do something different. And the only way to address this problem really is to make more assumptions, to create a model. So what we need to do is to come up with a generative model that relates the prompt to the final report. So you cannot do like we did before, where we did not make any assumptions. We just said each yi is a separate random variable. Forget about understanding the correlations and just using that simple model. Here you need to make some assumptions. You need to create a model, because otherwise there is no way of addressing this question. As usual, when you make assumptions, if the assumptions are wrong, you create a big bias, and this is what we were discussing before, the counterfactual estimate that you will get will be not very good. Right? On the other hand, if you don't make any assumptions, there is just no way of proceeding, because the variance will be so large, right? Because if you cannot possibly train a model for every prompt, you will have one data point for every model, right? So the variance will be huge. So there is a trade-off here, which relates to your question earlier, right? We need to make some assumptions, maybe assume a digital twin of the system, and the extent to which our answers will be correct depends on the quality of those assumptions. But you do need to make some assumptions, otherwise there is no way of making any progress. And so what type of assumptions are made in counterfactual analysis? And this is again a huge topic. There are books and books written about this topic, some good, some not so good. The models that are used are called structural causal models, or SCMs. These are basically graphical models. If you know Bayesian networks or Markov networks, it's in that class of models. And I just want to give you a sense of how this works. In order to give you a sense, I'm going to go back to the previous section because it's much simpler. I'll show you what to do in the agentic case. In the agentic case, we have a lot of variables. We have all the tokens of the prompt, all the tokens of the report, lots of variables. In the previous section, we had just 3 variables. I'm going to show you how an SCM may look like for the previous section setting, and then I'll show you how it can look like in the agentic setting. Okay? The key idea in an SCM is that for every variable, you include a node in your graph. So any variable that you have in your system, a node. And then you create edges whenever one variable functionally affects another variable. And you also need to include exogenous variables, exogenous noise variables, to account for randomness. Okay, so let me show you how this works. And again, go back to the previous section, right? So there we have three variables, x, a, and y. The context, the action, the app that you take, and the KPI. So an SCM there, which we did not have to assume there, right? But if I wanted to assume an SCM, I could assume it to look like this, right? So I could say, okay, based on the context, a policy selects the app. So I add an arrow to say that there is this functional dependence, right? And so that's this one. So the app depends on the context. Since this is a function, and I want this to be random, I also add some random noise, which I call u. So all the randomness is in this exogenous noise. Okay, then the KPI depends on the app that I choose and on the context. So I put these two errors, right? And I can say that the KPI is a function of the app and of the context and of some noise because there is randomness. So that would be an SCM for the previous setting. Once you, of course, how do you come up with this SCM? You need to make some assumptions, right? So, for instance, in the previous case, this would be the policy, so no assumption to be made. But for this one, it tells you what the KPI looks like under some context and action. You need a model. It could be a digital twin, it could be a world model, it could be a predictor that you train, it could be something that you know by domain knowledge, something that you train. But the point is that here you're forced to make some choices. In the potential outcomes framework, you don't make any choice. Here you have to come up with a generative model. Once you have that, the mechanism to do counterfactual inference follows 3 steps, which are very interesting, in my opinion, and very natural. And they work like this. So the first step is the technically called abduction. I don't know if you've ever heard about abduction. So abduction is in the same category as induction and deduction. But what abduction does is the following. So remember in the setting in the previous section, we have observed x, we have observed a, and we have observed y. That's the factual branch. Now in the abduction step, you try to estimate the noises. And the idea here is that you want to know what are the conditions under which that x, a, and y were realized. So this is the abduction step. So you estimate these variables u, and the idea is that you have this way estimated the hidden circumstances that created that particular outcome. And now, once you have that, for instance, if this is a simulator, this UI could be a random seed that you record. And then what you do is you force the app, the action to be what you like, so it's called intervention, and then you run your generative model. So the idea is that you have your simulator, for instance. The simulator has some sources of noise. You estimate the sources of noise based on the factual outcome. You fix those, and then you see what would have happened if I had chosen a different path. And that's the generation step. Now, I'm running out of time, but the same principle can apply in the agentic setting. In the agentic setting, the first thing you need is a counterfactual, an SCM. You need an SCM, so a structural causal model, for an agent, for an LLM. And it turns out you can do that. There is this nice paper. There are 2 papers that basically did the same thing. Comes up with a generative model for an LLM. And the idea is simply that you want to record, so in an LLM, where is the randomness? The randomness in an LLM is in the generation of the tokens. Right? So whenever you generate a token, you randomly sample from a distribution. So what you want is to have these exogenous variables that tell you how to sample the new token. And so what these authors did is they said, okay, once I have an SCM, these are the tokens I'm generating, and each token is generated using some randomness. Once I have that, if I record this randomness, I can then generate text in a counterfactual way. So it's a very interesting paper that I don't have now time to go through in detail, but what they did, for instance, is they took a text that some model generated, they changed some token, for instance here they changed the name of the character in the story, and then they compared two situations. One in which they just run the model again, anew, right, forgetting about what happened in the past. One in which they run it with the same noise, right, that underlay the generation of the original text. And what they show is that if you do this counterfactual generation, you get text that is much more similar to the original one. It's a more, really a counterfactual type of text. So what we did with Salvo is we applied this methodology to the whole system that includes also the network in the loop. And for that we had to come up with a model for this. So in our case, we used a simple digital twin based on MS3, but you can use any other model there. And we follow this whole procedure of abduction, intervention, and generation. And then we compare different methodologies to see, how we can obtain these counterfactual estimates. So we compare two different methodologies. One is you change your prompt and you run it on the actual system, but you run it anew. So you have your network, you make a different prompt, and you run it in the network, but in different conditions, right? In whatever conditions are happening now, right? And then we have one in which we run it on a simulated system, and then we have our method. It doesn't run it on the network anew, but instead records these, noise variables and then run the system. And the bottom line is that if you run these counterfactual generation methods, whether you look at the type of KPIs that you estimate in the text, in the report, or whether you look at the output in terms of the form of text, you get a much more, you get an output that is much more similar to what you have actually gotten you would have gotten in the real system had you been able to go back in time. So here what we did, we compared the output that we get, our counterfactual estimate, with what we would have gotten had we been able to go back in time, which we could do here because we had the whole system. If you're interested in this, we have a nice blog post on our INSI London website. We also have the paper. I'm also happy to discuss this with you. I can smell the pizza now, so I think it's time to stop. And so let me conclude. So I hope this gives you a sense of what you need to do if you want to reason counterfactually. I think these are very useful tools in general to have in your arsenal when you try to understand the performance of AI in a real system. As you saw, when they try to convey, it's not that straightforward to use them. There are some subtleties, and there are also different types of tools that you need depending on the setting. In some cases, you can get away with the potential outcomes framework. In some cases, you have to make some strong assumptions, come up with an SCM. And there are many other interesting problems, particularly in agentic settings. For instance, calibrating an agentic setting is an open problem. In the paper with Salvo, we had some ideas on how to solve this problem, but I think that's still kind of an open problem, right? So how to obtain those kind of confidence intervals they talked about in the first part is still quite unclear. Another interesting point is how you optimize digital twins or world models, knowing that you will be using them for counterfactual estimates, right? So should you design these systems in a particular way, maybe use a different type of training loss, knowing that later on you'll be using them to do some counterfactual inference. Okay, so with that, thank you very much for your attention.